Okay, so our next and last speaker for today is María Riveros from FAMAF, the University of Córdoba and CONICET. And she's going to talk about necessary conditions and the weight for maximal and integral operators with rough kernels. So, Silvina, go ahead.
Are you seeing well the presentation?
Yes, we are seeing the first slide.
And the
affiliation,
the hand, yes. Okay.
Your hand, yes.
Yes, my hand, because yes, the pointer.
Yeah.
I will be a little bit rough with my English also, so a lot of words in Spanish will go. Here, well, this is a joint work with Gonzalo Ibáñez Fircon and Raúl Vidal. Gonzalo was my last student that has made his PhD, and this work has recently been accepted in Studia. The talk, I will state the problem. I will state the problem. Then I will give some weights and results for a maximal operator that I will define in the talk. And finally, I will make some definitions and results for this general fractional operator. Well, I will be talking, we will be studying weights that are, as Shelly talked before, they are positive measures, and the operator that I will be considering is the following. We will integrate a function f with a kernel, and this kernel will be the product of different k sub 1, k sub m kernels. And here observe that it's not of convolution, but inside each kernel it appears a matrix n times n that will be invertible. These kernels will satisfy some certain Hormander condition and size condition. So let's make a little bit of history of this kind of operators. Ricci and Sjögren were studying a family of maximal operators in the Heisenberg group, and this kind of operator appears to them, and they studied a boundedness from L2 to L2 of this operator in R is defined. Observe that here the matrix is minus the identity, and here is the identity. And they study the boundaries of this operator from L2 to L2 respect the Lebesgue measure. Since then, different authors studied several problems with this kind of operators. For example, boundaries from LP to LP respect to the Lebesgue measure, changing weighted Lebesgue measure also in variable spaces, changing the kind of what do we ask to the kernel, for example, well, different things in BMO, strong and weak boundedness, well, several problems. And now I want to start telling more or less what I want to state the problem. Wait. So let's take alpha, a number greater equal to 0 and less than n. Alpha sub I will be numbers such that when I sum up, they give n minus alpha. The matrices will be invertible, and also the difference will ask to be invertible. So once at the beginning, we start with Marta Urciolo studying this operator, and we consider this kernel K sub I, like the fractional operator. So when we start starting studying the boundedness of the operator, the first thing we did, we start we obtain a Koifman-Pfefferman inequality. What is this? We obtain a bound from LQ to LQ of the operator. Here appears a sum of maximal fractional operators. I will define it soon. And the weight W to the power of Q, we have to ask that it has to be in A infinity, no? To have this here, to prove this inequality, we go via the sharp operator. After we obtain a sharp, we control by the sharp operator the fractional operator, then continuing as in a standard way, we have this inequality. But we have to ask the weight W to the power of Q is in an infinity. So this maximal operator, which is, if you see, is like the fractional maximal operator, but instead of being evaluated in X, is in the is evaluated in this matrix A to -1 X. So, for example, no, if I want to continue this inequality, I want to continue what this is less equal to, for example. So, as I said, the definition of this operator here, if I make a change of variable, the matrix here, I can change it to the weight, no? So if I add something to the weight, I will continue this boundness. And for example, if I ask that the weight W in AX is less equal to a constant, W in X here will say, I will say W has an homogeneity condition, no? Something like that. And if I ask the weights P and Q be as usual, and W is in the IPQ class, this is the good weights for the fractional maximal operator, then I can continue this inequality and I obtain a bound for the fractional operator, but with the matrix. So in the first inequality, I obtain a bound for the fractional this fractional operator. So I have asked first W to be in the class APQ and this homogeneity in the weight for all the matrix A sub I that appears in the kernel. So here is one of the first question that involves this work. One of the question is, do we have good weights for this fractional maximal operator? Because here we had to go through the APQ classes and ask this homogeneity condition on the weight. So is there a characterization of the weights for this maximal fractional operator? If we have this characterization, if we are able to find this characterization, are we able to get a bound for the operator, the strong PQ weighted inequality for the fractional operator? And when we were working, as I told you before, to get this boundness recently, we used the Koifman-Pfefferman inequality, and here we have to ask W to the power of Q being infinity. Can we avoid this condition? Well, this will be several of the questions that we start to make. We got some answers, not all of them, but one for example, to get the answer, for example, for 2 and 3, we will use the sparse domination of an operator, and we will introduce a sparse domination suitable for this operator T sub alpha m. So let's start with the fractional maximal operator given by this matrix A. We will consider this, and we will define these following classes of weight. I say, we used to say these are the Marta's weight, Marta Urciolo, because she started, well, Marta worked a lot of time, for a long time with us in several works with me and Gonzalo, Lucas, well, with all the group of FAMAF. She has recently retired. So we like to say Marta's weight. She settled these weights, and if you observe, they are like the EPQ classes. But the difference is that in this average here, when we are taking this average, we have W sub A, where W sub A in X is W in AX. So this will be the classes A sub A PQ, and in particular, we will put also the classes A sub AP when W to the 1 over P is in the APP. Observe also that if A is equal to the identity, this is the class APQ, no? The one that we know for the fractional operator. So the first result we obtained was a weak type PQ characterization. This is the alpha is great equal to 0 and less than n, p greater than great equal than 1 and less than n over alpha, and q satisfies this equality. The maximal operator is of weak type LP, LQ, if and only if the weight is in this class of weight. It is in the class A sub APQ. And also we have a control of the constant of the operator. No, the proof of these theorems is very similar, or follow the step of the one from Mackenhaupt or Mackenhaupt-Widen in the classical, and the weights appears naturally. So if you follow the proof of the classical one, is very similar. You have to have some details in mind, but it's similar. So one of the things that appears here that the difficult is that when we are trying to take the same properties as the Mackenhaupt weight, one of the things that we say, we are going to be able to have an A infinity with an A sub A infinity, for example, class. One thing that we have, the problem is that we are not integrating in the same cube in the both averages. Observe, while we want to control this product, this one, when we have W sub A, if you do a change of variable, here we're integrating in A times Q, no? And here in Q. And maybe this is not a cube. Is not a cube with the lados paralelos a los ejes. No, it's not a standard cube that we use. So, for example, let's give some examples. If we have a rotation in p over 4, no, the cube transformed to this cube that is not the standard that we use to calculate a class of weights. Or, for example, if we have this matrix that is a dilation and a contraction, it transforms the cube in a rectangle, or this that will transform a cube into a parallelogram. So this is one of the first difficult that we had if we want to obtain all the same properties. But we, for example, the thing that we couldn't prove is the reverse Helder condition. No, we couldn't, and still now we don't have. So we cannot prove the strong PQ boundedness of the operator, no? But even though we had a lot of good results, for example, the first one, if the weight W belongs to this class of weights A sub APQ, then we have this homogeneity in the weight. W of AX is less equal a constant, the constant of the weight, WX. So this is a condition that appears naturally. Also, we have an increasing condition in the classes. No, this we have as the AP classes, they are increasing. We have like a factorization, but the obvious one, no? If this W series in this A1 class and in this W1 in this the other A1 class, then the product is in the A sub P class. We have also like a doubling condition with the matrix. Observe that here we use the weight W sub A, but here appears the W weight, no? But this it's useful in some terms. And also we have this following. Observe that if W belongs to this intersection, no, then W is in the AP classes, and we have this control of the content. So here we have like well, we have this conclusion. And also observe the following. If we have W is in the A sub AP class, over here. If W belongs to the AP class, then, and we have the condition, the homogeneity of the weight, then W belongs to the A sub AP. Here we have the things that we were asking before in the theorems imply this new condition. And so we have this inclusion, no? AP intersection, this condition is included in this new A sub AP. And also we have an if and only if, that is, if W belongs to this intersection, if and only if W belongs to the class IP, and W sub A is like W. We have the both inequalities. And now we will give, and here, observe that here we have an inclusion of AP plus this condition is in this new class. Now we will give another inclusion, a reverse. Here, maybe asking a lot for any inverse matrix is too much, no? So we have some conditions. For example, if we have a matrix such that is equal to its inverse, then if we have a weight in A sub AP, then the weight is in AP. And if we have, for example, a matrix that for some n, A to the n is equal to A, then also we have this inclusion, no? But asking something to the matrix. This is, if we ask this condition to the matrix, we have that A sub AP is a subset of AP. For example, if we have this an orthonormal matrix like this, we have this inclusion, or for example, the rotation in OP over 4, it also will satisfy this condition. So we were struggling, we wanted to prove the reverse Helder condition, we couldn't. And suddenly we say, well, if we think this as a two-weight problem, not as a one-weight problem, no? So for example, instead, and our two-weight will be W sub A, W. Well, so trying to, we pull up all Sawyer's background, no? And if we recall, what is the testing condition? If alpha is greater equal to 0 and less than n, and we have a pair of weights such that satisfies this condition, this will be the testing condition. So Sawyer proved an if and only if for the fractional maximal operator, but Moen proved a quantity version of this. So the result, the very well-known result, is that a pair AUV satisfies this testing condition if and only if we have a strong PQ inequality. So we adapt this two-weight condition for our problem. So we start putting what is the two-way, the testing problem with the matrix A. We will say that W is satisfies this testing condition if this pair of weights satisfies the Sawyer testing condition and the dual case. well, also if alpha is equal to 0, we put. So we have for this setting, if W belongs to this, satisfies the testing condition with the matrix A, if and only if we have this strong PQ inequality. And also we have a control in the constant. No? So another thing that we could prove is that if the weight W satisfies this testing condition, also the weight W belongs to this new class, Marta's class. So we have the following inclusions. The APQ class intersection, the homogeneity on the weight, it's included in the testing condition, is included in the Marta's weight. Now we have this inclusion. And also for the AP class. And now I want to give, let's consider this operator. I put with m equals to 2 for it's easier to write the things. Consider this operator, no? We will we'll have the following: is if alpha is greater equal to 0 and less than n, and alpha 1, alpha 2, when I sum it up is n minus alpha. Observe that here, when we sum up, here is it's a fractional operator if alpha is greater than 0, and if alpha is equal to 0, it's like a singular operator. I say like this singular because it's not singular, no? But it comports like. And we will ask that the matrix A1, A2 are invertible, and also the difference, E and W a weight. Then we have the following: if the operator is bounded from LP to LQ, then we have that the weight is in the intersection of these two classes. Here we have a necessary condition. And also we have like an if and only if we ask a little bit more. If we ask that the matrix A2, for example, is equal to A1 to the minus 1, or A1 is minus the identity and A2 is the identity, then we have an if and only if. The thing that if and only if, the going back, if W belongs to this class of weights and we ask this one of these two conditions on the matrix, then we have that W belongs to the APQ class traditional, and we recover the boundaries that we had before with asking all those things. I want to remark that these results contain a previous one that made Elida Ferreira and Guillermo Flores, that they consider this operator, but for P equals to Q, alpha equals to 0, and the power weights, and only these two matrices. So here we have a greater result. And also I like to think this like the Calderon-Singmunds operator, in the way that AP is also necessary, but you have to ask that the N Riesz transform are strong PP, no? Here our Riesz transform will be this special operator for this case. So I start speaking, or I start saying that we will speak about rough operators, and I didn't start even I will go fast. Well, here we introduce some size and Horn-Mandel condition. Well, here is the average that Shelby maybe used before. If we have a number R greater equal than 1, we have this average, and we will also use this when we are speaking like this average, but we are taking in the average like in a crown or in a ring. I don't know how to say in English, in a ring, no? And we will use that a kernel K sub alpha satisfies a size condition if when we integrate the kernel in this ring like of size t is less equal to a constant to t to the alpha minus n. And observe that if R is equal to 1, then the kernel satisfies this inequality, and if alpha is equal to 0, we will write SR. This is a size condition that is very we need a lot this in the theorems. And what is the L alpha R Hormander condition is, well, we ask that the kernel satisfies this size while integrating far of the zero. Observe that if you put here alpha equal to 0 and R equal to 1 is the classical Hormander condition, the usual. And also we can change R by infinity, and here we will put the norm infinity of the kernel. And yes, observe something, that if k sub alpha is equal to modulo to this kernel, then we obtain the fractional integral operator, and the E alpha satisfies this size condition and this Hormander condition with infinity. No? So in the following theorems, we will consider the following hypothesis. I will put it all in one. We will have M kernels. Alpha will be a number great equal to 0 and less than n. M will be a natural number. Alpha 1 to alpha m will be such that we sum it and it's n minus alpha. R sub I will be a number here satisfying this condition, and K sub I, the kernels, will satisfy this size Hormander condition, and this size Hormander condition, and this Hormander condition. Observe that for K sub I, it's related to alpha I and R sub I. And also the matrix will be invertible, and the difference also invertible. And in the case that we are considering alpha equals to 0, we will ask that the operator is strong type P0, P0, respect the Lebesgue measure, and we'll be considering the exponent S that will be the conjugate of all the R1, Rm. Here, because we will be considering, we will be doing in the proof of the theorems a lot of Helder inequalities. So the first theorem, before the first theorem, we will have to recall what is, if we have a dyadic lattice D, we say that a collection of cube Q is a sparse family, a eta sparse family, if there exists a number eta in between 0 and 1, such that every cube Q in S, for every cube Q in S, there exists a measurable subset E sub Q, such that it satisfies this with the measure between E sub Q and the cube Q, and this E sub Q are pairwise disjoint. So I will start presenting the sparse domination of the operator. There exists a constant C and 3 to the n, this eta sparse family, such that the operator is controlled by this 3 to the n, but these several sparse operator, where these sparse operator are defined in the following way. Observe, for each for each J, for each A sub A matrix, this sparse operator is this average. Observe that it appears here the S, that is the conjugate number of all the exponents R1 to Rn. This is a pointwise estimation of our operator, no? And if we want to get a bound of this operator in a weighted bound, we will have to get a weighted bound for the sparse family. Oh, I want to remark that here appears the number S, that is the conjugate number that of all the R1 to Rn. And so here we have to introduce a very not difficult, but in testing condition that is suitable for pair of weights. This was introduced by Lacey, Sawyer, and Uriarte Tuero, and they introduced this testing condition for a dyadic lattice. Observe that here appears the word out, and it because you have the dyadic lattice, you take a cube R, and here you take all the sum of over all the cubes that contains the cube R, and then you take the supremum from all the cube R in D, and this is this star is the conjugated one. And here we also put the matrix A. Observe where appears the matrix. And also in the case that we take the matrix A equals to the identity, well, we write without the matrix. So the first result for the sparse operator is the following. If we have a sparse family from a dyadic lattice, and let UV be a pair of weights, such and sigma we define in this way, if UV satisfies the local testing condition and these constants are finite, then we have this bound of this pair of weight, U sigma, where sigma have to be with the weight P. So if you choose U equals to W sub A to the power of Q and V this weight, we have a boundedness from LP to LQ of the sparse operator. So for the operator, we have the following theorem. If we have a pair of weights such that any dyadic lattice D, the testing conditions are finite, then we have the bound of the pair of weights U sigma. And here we had to ask for every dyadic lattice. It's kind of strong, but it would be useful. Observe the following. So here we did it very general for the operator satisfying the general Hormander condition with the R sub I, the rough condition for all the kernels, and for any matrix. Now, if we start asking something for the matrix, for example, if we ask that one of the matrices is equal to another, is equal to the inverse of another matrix, of the M matrix that I have, and WS belongs to the intersection of these A sub A, PQS classes of weight, then we have an LQ LP boundness, LQ boundness, and with a control in the, also we have a control in the constant of the weight. This appears because we can obtain this for the sparse operator. I want to insist again that if we ask this condition in the matrix and W belongs to Marta's classes of weight, then W to the power of S is in the APQ class standard class of weight. And here we have a result, a previous result that we made with Gonzalo and Raul, that we studied this sparse operator when we were considered a fractional operator with the kernel in the HR alpha condition, in that Hormander condition. We study first that problem, and then we start with this matrix problem. So here we choose, we change the matrix, but if we change the operator, the kernel, if we ask that is in this smoother class, then we will have a better result. Observe first that if we have the pair of weights satisfies the Sawyer condition, and this pair of weights satisfies the dual Sawyer condition, then we will have the testing condition, the local testing condition will be finite for any lattice D. So we have the following two-weight condition for the operator. In this case, now when the kernel satisfies this size and Hormander condition. So we have for any P less equal to Q, we have the LP, LQ boundedness for any BU. And then if we ask a little bit more, if we ask that the pair of weights UV is this one, the original, the one that we started, and we ask that the weight W belongs to this intersection, then the operator is bounded from LP to LQ. And here I want to highlight that if we ask a weight to be in this intersection, then W will be in Marta's classes of weights and will satisfy this homogeneity condition in the weight. And before we start asking W in the APQ classes of weights, and we ask this condition. So we are proving in this corollary another way to prove the theorem that we prove in this year, in 2014, but without using that the weight is in infinity or in the APQ classes, changing the problem as like a two-weight problem. And that's all I had to tell. Thank you very much. And in Cordobés.
Okay. Muchas gracias. Thank you very much.
Gracias.
Thank you very much for a very nice talk. And we don't have any problem with the time. So if one has a question,
I have the lomitos coming, but
okay. Okay, dinner's ready. So we all need to go finish cooking for the family. So any questions here? I have one question, but a very basic question about the maximal function. So, the maximal function for the case P. Ursula, is there? Ah, okay.
Yes, it was
the maximal function for the case P equal to Q and alpha equal to 0. Just the maximal function modulated by this matrix A to the -1. So you cannot prove reverse Hölder inequality.
No.
So what about the strong P bound for this maximal function?
No, it's the same, because we could, well, maybe because we try to do it as the usual way, maybe there is another way to prove it.
Yeah, of course, using you cannot prove.
We cannot go back if we have we don't have P minus epsilon.
Exactly.
We don't have
the open property. Yeah.
Yes, we don't have the open property. We don't have reverse Hölder condition. We don't have an infinity.
And what about the weak? The weak inequality.
The weak, yes, is if and only if. Here.
Maybe I missed it.
Yes, here maybe why maybe I pass it. Here.
Okay.
There is there appear the weights. There you know that they are necessary and sufficient condition for the weak. No, the weak.
Yeah. Okay.
Yes. We made a lot of people think, Carlos, Perez, Shelby.
To think about the reverse Hölder inequality?
Someone came and we said, I think about this problem. Now, maybe if you choose particular cases of matrix, we go back to this usual case. So maybe it's not so interesting. Not so interesting, no?
Okay. Any other question?
Can I ask you something, Silvina? So you said the reversal, but and you also said, well, the A infinity, but did you does the union of the AP?
No,
Is it something
you can,
interesting or?
Yes, you can put, but sometimes you use A infinity going backwards. No, if a W is in A infinity, then is in
one of the APs, but
yes, and that is P minus epsilon, and so
yes. But I thought, yeah. So you don't have the self-improving property.
No, that was and it is the thing that we are integrating in different.
I thought you, but I think you said the one, yes, so the side that if you're in AP, then you are in larger ones, but you cannot.
Yes. No, we cannot go back. And here, if you see, we are not integrating in the same.
That makes it completely.
When I start thinking this, I start thinking that is very similar when you have the lateral AP classes. Right. They work very similar in some things. And I want to reproduce things of that, but I couldn't. No, it's difficult. Well, for me it was difficult. I couldn't. So well.
Great. Any other question or comment? So if not, let's thank Silvina again for a very nice talk. So thank you very much. And that's it, right, for today.